Good morning, everyone. The room is a bit emptier, so thanks for coming. And so today there's going to be, let's say, 2.5 talks. First, I'll very briefly talk about what else there is beyond like post-quantum key encapsulation and the digital signatures. Then we'll go a bit more into depth about my favorite topic, fully homomorphic encryption. And then there's going to be, again, coffee break. And then Lorenz is going to talk about advances in isogenies. I'm going to start slowly. And this is already a question to you. Just make some guesses. What else do we need beyond KEMs and digital signatures? No, I know some people know. One example, like, have you ever heard of like fancier crypto? Yes. Very good. Some examples. What else? You in COSIC, you know. Well, for example, just multi-party computation. In general, a pretty long list. So you also need post-quantum key agreement protocols, MPC, so multi-party computation, that's going to be very briefly explained, and also zero-knowledge proofs and a bunch of other stuff. Like, there's also ring signatures, like more fancier signatures. But this is kind of a non-exhaustive list. And to an extent, they've already been implemented. So for example, Signal and iMessage, they implemented post-quantum key agreements, and Signal also has their ratcheting stuff. Browsers, web servers, they also need a bunch of specialized post-quantum techniques that previously relied on non-post-quantum crypto, and now needs to be swapped out and sometimes also augmented because some protocols may not be secure in a post-quantum setting. Now, this is like an informal definition of MPC. You have a set of parties. They want to kind of compute a joint function on individual inputs, but they don't fully trust each other. And roughly speaking, there's like two models. You have just like semi-honest and a malicious setting. Semi-honest setting just means people will look and try to infer stuff based on the communication. Malicious MPC means they will actively try to interfere and break the protocol. Like a kind of cute application of this is you have a group of friends or people try to figure out who's the richest, and they don't necessarily just want to say how much they have in their bank account. So with MPC, they could just plug in like a shared or encrypted version of their wealth, and ultimately they just get an output determining who the richest person is. That's the gist. Then another primitive in general is called oblivious transfer. Just effectively you choose a value. And so a lot of OT protocols may not be post-quantum secure, and so they also kind of need to be optimized for that setting. And this is like a general path which you can look at later. Not going to bore you too much with protocols. All right, so small warning. There will be a lot of math on slides. The math is not going to be difficult. Mostly addition, multiplication, model number. But I structured this presentation in such a way that, based on the slides, you can implement this FHE scheme I'm going to describe. So, first, what the hell is FHE? The idea is kind of, well, you have your normal encryption scheme, you can encrypt, decrypt, maybe a bit more. But now you have fancy encryption, where you can also perform computation on the encrypted data. So for example, you have some user that can encrypt their medical data, send it to some biotech company or server, whatever. They can run their analysis on the encrypted data. Eventually, you get the encrypted result back, and you can decrypt. Pretty neat, because the company then kind of gets to keep their trade secrets, more or less, more on that later. And you don't leak your medical data. It's quite cute. Now, if you want to do it in a more formal way, this is your generic definition of a ring homomorphism. So basically, the addition or multiplication in the F gets pulled outside. And if you do this with FHE, all that happens is you substitute this F with an encryption function. Though the multiplication and addition, they're going to be a bit more difficult. A kind of a implicit thing, although there are FHE schemes, kind of under the hood, they will use lattices. So there's still going to be like an approximate component. All right. Now about some history. Now, we won't discuss RSA too much. But if you remember, the encryption for RSA is just you raise it to some power. So at least in theory, you can multiply two encryptions in RSA and get an encryption of the product. In practice, this wouldn't work, because to keep RSA secure, you would need some padding, and the product would kind of mess that up. There was other schemes, like if you have the Payet or Al-Gamal, they're either additively or multiplicatively homomorphic. Now, some more history. The actual first FHE scheme was only created in 2009 by Craig Gentry, his PhD thesis. Now, although it was the first construction, it was completely impractical. Just evaluating a single NAND gate, like people implement this, and it took like, I think, 3,000 hours. Now, there's modern schemes. This is also not exhaustive, but like these are the big ones people will have heard of maybe. TFHE, there you tend to encrypt like, say, 4 or 5-bit values and work on those. There's this class of schemes, also called SIMD schemes, where you encrypt vectors of data that are also bigger. CKS, similar. They can encrypt even bigger values, but in a sense, it's approximate. But we'll go through all of these families more or less, and especially this class we're going to look at in detail. Modern research, well, kind of still focus on improving efficiency primarily. So for example, in time complexity, in good cases, you only have a 10 times slowdown compared to the non-encrypted version. But I can easily pull out examples where the slowdown is like 9 orders of magnitude. But that's not great. Right. So this is the outline. The second part is going to be the biggest one, because I'm really going to show you how this TFHE scheme or FHEW scheme is going to be constructed. This is going to be a bit more high level, but the idea is actually quite similar. And the last part is like more practical considerations, like what do you need to think about when using FHE, what libraries there are, and how do you not mess up security. So without further ado, some background, though I'm going to skip a lot, because we've seen a lot of these things in the previous lectures. So ultimately, this is most of the math you're going to need for this talk. So if you still know like addition or multiplication mod Q, you will have no issues. If we work in these polynomial rings, this is not fully mathematically correct, but intuitively it just means we work mod this polynomial. So like you would do normal polynomial division and take the remainder. Now for FHE, in general for lattices, what you usually use for these polynomials are so-called cyclotomic polynomials. And they're just kind of defined as this. And the nicest ones are the cyclotomics with a power of 2 index, because then they just look like this. And they're also very easy to reduce modulo, because then just x to the n is just -1. Just you have a small example here. If you then work, you have this 4xn, you reduce it mod 5m, just get this back. And for this talk, you can always assume m is going to be a power of 2. There'll be no exceptions to this. Otherwise, well, we already had a talk on fast polynomial multiplication, so I'm going to very briefly go through it. Because in FHE, you tend to work with polynomials with degree 2 to 12, 2 to 17. The other day, I was working with 2 to 20. So if you use like something like a naive algorithm, you will wait a long time. Again, we talked about this. There's Karatsuba-like methods that can get it down quite a lot. In general, FFT-based approaches are going to be the fastest. Euler's convolution theorem, again, Super talked about that. Like this is just a different perspective on entities, which we didn't really see. Basically, the DFT, you just described it usually as this, with a 2n root of unity. And you can use the exact same blueprint to compute the entity. And then to get the O and log n complexity, you just apply whatever FFT algorithm you want, like that. Now lattices, we've talked enough about, so I'm not going to dwell too much on this. So lattice, in your mind, grid. And then there's a bunch of applications, again, of lattices. We mostly care about crypto, but they're also using crystallography and factoring. And then, yeah, we don't care. These are the usual problems, yada, yada, yada. And now we actually get to the fun part. Now, we've already talked about this, but I just want to make sure that at least some people listened. So again, we have this nice linear system. Is it easy to solve? At this point, most people should be able to answer this. No, not you. You already answered. Oh, yeah. Is it easy? Yeah. What would you do? Gaussian elimination. Yep. Okay, if we trick it, we got an error. What did we see? Easy, hard, it depends. Who's going to be a victim? Do you know?
Probably depends
on just exactly. So if you choose all your parameters correctly, this is going to be quite hard. And so like the theory definition of this is you have this thing that induces a distribution, and you have the decisional assumption, which is to say distinguishing this LWE distribution from uniform at random over the space is difficult. There's also a computational assumption where it's kind of similar, just we have samples from the distribution. I need to recover the secret. And both of these are assumed to be hard. So this is what we usually mean by difficult. Right? You can play the same game of ring learning with errors. And we focus mostly on module LWE. Ring LWE is actually a special case, simply. There, instead of sampling just a vector, we sample polynomials. Now the secret is also polynomial. Multiply the two, add an error. And the, let's say, hardness assumptions, they just carry over. You just replace the LWE by ring LWE. And again, like module LWE we saw, there's also variant binary LWE and sparse LWE, but we don't really need those. Is everyone still with me? Are we awake? I see people nodding their heads. That's great. So a nice property is actually to say, OK, so first, let's say we have an LWE sample of some value, which just means we construct an LWE sample, and we add our value or message to this side. And so to recover this, or rather invert it to an extent, we just recompute this difference. And for ring LWE, you can do the same, though what you're going to plug in is a polynomial now, not just a scalar, like an integer. And the same relationship holds. And kind of a funny question to ask is, if you have a ring LWE sample, can we just derive an LWE sample for one of the coefficients of this polynomial? The answer is yes. So very briefly, say you have a ring LWE sample as this, so a tuple of two polynomials. And let's say now we construct a coefficient vector simply of this polynomial, and do the same for the secret. What you can kind of show is that for any index of the message, you can construct a permutation matrix that's going to be ternary, though, such that this thing holds. And the idea now is just to point out then, well, if you consider now this tuple of vector and scalar, you can actually check this is going to be a valid LWE sample of mi. Kind of give you an example. You can either go through this on your own. We very quickly go through it now. So we have a ring LWE sample of the zero message, and we don't assume noise, because we don't really care about that. And yeah, these are the coefficient vectors of these polynomials, so that's quite straightforward. For the constant term, the matrix would look like this. And then either in your head or later at home, you can check that this is going to be true. And the kind of point of this is to say, if I give you a ring LWE sample at any point, you can transform it into a LWE sample of one of the indices. And we will need that later. And the kind of intuition as to why it works is, well, you have some polynomial, we multiply it by a monomial. You will, in the ring we're in, rotate the coefficients up to sign flips. Right? Now, let's come to the fun part. We want to design an FHE scheme. So the primary thing we're going to expect is we have a scheme with which we can do unlimited computation. There's two ways to approach this. One way is to say we created an encryption scheme with which we can do arbitrary additions or multiplications. Someone more invested in computer science, though, might say, or we somehow create a scheme that can evaluate a NAND gate. These are equivalent in practice. Now, if you look at like more theoretical FHE papers, they will maybe nitpick a bit here, because what I didn't include here is whether the functional circuit we're evaluating with the scheme is going to be known in advance or not. But we don't do theory right now, so we don't care. All right, so kind of what is the setup? Actually, there's a slide missing, but anyway. So to encrypt values, what we're going to use is the whole regaf paradigm, which we already saw a few times. So for key generation, all we do, pick our parameters, choose our secret vector, and that's it. To encrypt, create an LW sample. So again, just tuple a vector scalar, add the message, except we actually don't. We need to scale it again. And this is maybe easier to understand through the decryption function, because when you decrypt, you're going to subtract, again, the inner product. And if we don't have the scaling here, there would be no way of telling the message and the error apart. So we encode the message. This is one way to do it. There's also other ways, but this is the easier one. And then during decryption, if you do this rounding correctly, you get a message back, provided the error was small enough. And this is going to be the most annoying part. Now, let's actually do some homomorphic stuff. First thing, I already mentioned this in my last talk, regaf ciphertexts are additively homomorphic. So say you have two encryptions, and you just add them component-wise. You end up with this big term here. Since the inner product is linear in one component, this just goes in, which means we have an LW of the sum, well, scaled sum, which is equal to the encryption, right? What's the issue here? There is an issue between the second to last and last step. You're smiling, you seem to know what's going on.
The error occurs.
Exactly. Yeah. For the encryption to work, we need to have this bound. But like in general, why would that hold? And again, this is going to bother us for a long time. It's going to be the topic of most of this talk. So yeah, here we saw addition, but we also, since we can do addition, we can do scalar multiplication. And then your error might just explode if you're not careful. So as we just said, decryption can fail if the error is too big. Another issue is we can only kind of encrypt values between a 0 and a t because we need to scale. And we only see an addition, like we also care about multiplication, no? And so to kind of fix this, we need to switch the setting a bit. And we're going to go to ring LWE. All I've said previously is still going to hold. Some differences, though, like the set of scalars is not just like some integers mod q. Set of scalars is now these polynomials. So first definition now, gadget vectors. Sounds fancy, it's very easy. For modulus and basis, gadget vector is just going to be the power of that basis up until, yeah, the log here. It's sometimes called the number of digits. Why is that useful? Because now we also want to do gadget decomposition, which again sounds fancy, but it boils down to do basis decomposition with regards to L. So if you have a vector V, we're going to do basis decomposition of L with regards to big L in each component. It's going to give us this set of vectors. And it's fairly easy to see that if you then multiply by the gadget vector, you just get the original vector back. And for polynomials, we do this on the coefficient vector. The polynomial. Now, just very small example, just to make sure everyone got it. So for these parameters, the gadget vector are just the powers of 4. And then if we decompose this vector here, we obtain these 3. And then on your own, you can verify that this holds. This is quite easy to see. Any questions up to this point? OK. Well, OK, a lot of stuff happening, but it's not going to be difficult. Now, we've seen previously we can just scale this, or rather scale the message, plug it into ring LWE, and we would hypothetically have encryption. But now, depending on who you ask, this is called ring LWE prime or gadget ring LWE, whatever. We're going to encrypt a message with regards to a gadget, which means it's a vector of ring LWE samples, where the message is first multiplied by the first entry of the gadget, second entry of the gadget, etc. Now, to multiply this ring LWE prime with a polynomial, we're going to apply the gadget decomposition on this polynomial, and then compute this thing. So effectively, the inner product of these two vectors. And as you can see, since ring LWE is homomorphic, these polynomials will slip inside. And in the inside, we have kind of the reconstruction of P. So ultimately, we have a ring LWE of the product. Can anyone guess what's the point of this? Because like this just adds complexity, so surely there must be a reason. I'll take any guess. Just want to hear someone talk. Do you know? OK. Go ahead. OK, why? Exactly. So first point, each of these ring LWE samples will give you some information about the message. More importantly, if you decompose this polynomial, you will be able to better bound the infinity norm of the coefficient vector. So just to illustrate this a bit, say your error is sampled from some Gaussian, so the variance in the coefficient is equal to this. If we didn't use ring LWE prime and looked at the error of the product here, so E prime is just going to be the previous error times the polynomial. And if you then actually check the variance of the coefficients, proportional to the square of the modulus, if you can't make any assumption on P, and this is effectively impossible to decrypt afterwards. If you use gadget LWE or ring LWE prime, then your E prime is going to rather look like this, because we're multiplying the individual errors plus the decomposed polynomial. The variance is then going to be proportional to this. To give you like a concrete instantiation of what that means, for L equals 2 and a 64-bit modulus, if we don't use it, this is the variance of the error. If we do, significantly smaller one. So that's quite important, because now we're immediately going to extend it to something called ring JSW. And it's just a tuple of two ring LWE prime, one of which contains the message, the other one, the message times the secret key, or negated secret key. And fun thing now is we can take these ring JSWs and multiply them with ring LWEs. What we do is just we apply this gadget product component-wise and add the two as this. And if you actually write it out fully, what you'll see is, well, here we compute this product again. This slips inside. Then ring LWE is additively homomorphic. So again, the things inside the bracket keeps on going inside. Eventually here we just kind of decrypt in the ring LWE. So we end up with the product of what was in the ring JSW and in the ring LWE. Now I've kind of omitted this new error term, but it just is, if you pick all these parameters, so the gadget basis, etc., properly, this will remain rather small. The bigger issue here is the error dependency on the message. But we'll find a way to kind of cheat our way out of this. Some other notes about ring GSW samples. So, well, we just saw that we can multiply them with ring LWEs. Another thing is we can actually multiply them with each other. How that would work is a ring GSW sample, if you want, is a matrix of ring LWEs. And so you would apply this product to each entry of the other ring GSW, and you can show that this will yield a ring GSW of the product. And also by construction, they're additively homomorphic. Or maybe as a fun fact, but that's not really important, you can think about it. You can create ring GSWs of values without knowing the secret key. Think about this because it seems kind of like a big claim. But you absolutely can. I'm not going to tell you how. OK. So far, it may feel like I've misled you. Because so far, what you could say is we are going down the avenue of trying to determine an FHE scheme where we add and multiply values. But we're actually not going to do that. We will actually go down the route of evaluating a NAND gate. Now, why can't we just go on with ring GSWs? Hypothetically, we can. There's a way to augment them to something fully homomorphic. It is impractical. It's extremely efficient to the point where I have yet to see an implementation. Because ultimately, noise still keeps growing. So like we can multiply ring GSWs, but our noise will keep on getting bigger and bigger. So this is somewhat annoying. Which leads us now to the notion of bootstrapping. So informally, you have some FHE scheme and a ciphertext, and you know some kind of bound on an error, be it in terms of variance or some other metric. What the bootstrapping procedure is going to do is going to somehow output another ciphertext that decrypts to the same value, but with lower noise. This sounds nice, because if we can design such a procedure, we can do our computation. Once we know that the error is about to become too big, we apply this bootstrapping and just continue. So the general approach to do this, but this is not a universal thing, there are exceptions. You're just going to somehow homomorphically evaluate the decryption function of your original FHE scheme using a possibly different FHE or just HE scheme. Important note, to make this whole outsourcing of computation feasible, anyone should be able to do it. Like, people shouldn't need a secret key to do it, otherwise there's no point to the whole exercise. So, very small outline, which I hope everyone can read. What are we going to do? To encrypt values, we're still going to use the regaf ciphertext we saw at the very beginning. We're going to use the ring GSW samples to create a bootstrapping procedure. The ultimate question is now how. So let's see our ingredient list. So first, we're going to fix all the parameters again. So the smaller ones, they're going to be LW parameters. Now, to make the whole exposition a bit easier, we're going to assume that the secret is binary. In practice, this has little to no effect on security. For ring LW, capital letters, and as a kind of specific thing, we're going to assume that the LW modulus Q is equal to 2 times n. Can people maybe guess why? Or rather, why 2n? Why not just fix it to n? It has something to do with the property of the ring we're in. No? Well, we'll see that in a moment. So some more or less important observations first. Now, decryption of regaf samples is linear up to the rounding part, because we just compute a linear product with a known vector. Now, computing is a product in our case. We only need additions. Is that clear? Why? Look at this. You're nodding your head. Why? Exactly, since we just have a 0, 1 vector, we either add or we don't. This is also quite useful. Some hot takes. If you have a regaf sample of encryption, and I give you the encryption, well, anyone can see its components. Like, it's kind of the point of encryption. But in the next few slides, you'll see this is somewhat a non-trivial observation. Even less surprising, if you multiply monomials, you're going to add the exponent. I hope you don't think I'm insane by pointing all of these things out. But so first, some more definitions. If you have a ring GSW sample of some bit, you can homomorphically evaluate the max gate by just computing this term. So this is the ring GSW ring LRB product I mentioned earlier. Now, briefly, why does this work? Let's forget about the FHE entirely. What we're doing here is effectively computing this term. It's kind of easy to see if your bit is 0, it just returns P0. If your bit is 1, it's P1. Okay? And again, if you choose your parameters for the ring GSW, etc. properly, the noise is going to be so small that when you decrypt, this will work without issues. Then, another definition, I love those. So for blind rotation, this is a very common term. So what you'll have in terms of key material, these are the special keys you need for FHE, an evaluation key, which is just encryptions of the coefficients of your secret. So since we said SI is either 0 or 1, this is just a bunch of encryptions of bits. Nothing you need for blind rotation is some LRB ciphertext. And finally, you will need something often called an accumulator, test vector, rotation polynomial. There's a bunch of names, and no one really agrees. So what this blind rotation procedure is going to output? It's going to output a ring LRB sample of this polynomial here in the accumulator times, and if you look at this, this is the negated decryption of the LWE sample. If you look at this now, can you now tell me why Q needs to be equal to 2n? So maybe it's on the next slide. Do we still remember in what ring we are in for the polynomials? Anyone? Okay, then where's the last slide? I mentioned this. Okay, we're almost there. This ring here. What's the order of x? Does in, like, what power do I need to raise x to get 1? You're smiling, so you know. Exactly. So do you know? Maybe can you see why later we needed this requirement? Okay, then. So if we don't set q equals to 2n, this would not make no sense. Because we assume our LME modulus is 2n, and this is equal to the order, which means that, like, if we actually compute this, or rather, if we compute the exponent without modular reduction, there's this term like k times 2n. But since the order of x is 2n, this is going to get removed. So this is why we roughly need this requirement, though you can circumvent it in ways, but this is not interesting for us. So how does this whole thing work? This is actually quite straightforward. So first we set up the initial new accumulator, and we just keep on evaluate the max gate we just saw. Because the max gate contains the encryption of the bits. So iteratively, we just apply the max gate over every ring GSW sample. Why this works is, if we look at what we're actually computing, what this is going to output is a ring LRB sample either of the previous accumulator, if S is 0, or the current accumulator times x to the AI. And inductively, if you extrapolate, eventually you end up with the initial accumulator times the sum of these. And then, okay. Finally, you can also multiply then just by x to the minus b. And then you eventually end up with this. Now, a small interlude. We can, in a way, evaluate lookup tables with monomials. So just to explain this a bit, I've switched the ring. This is somewhat easy to work with, because now we have just x to the n equals 1. So say you encode your lookup table into the coefficients of a polynomial. And then you start multiplying by some monomials. What happens is we're going to rotate the coefficient vector. So ultimately, the constant term of the result is always going to be the ith coefficient of the original polynomial. This is kind of the observation here. This is nice, but it's not the ring we work in. Ring we work in, what's going to happen? Actually, we're going to have sign flips. This is kind of annoying, because now the constant term is either equal to the index, like the value at the index of the polynomial, or the negated value. And so we can then, if the lookup tables we can evaluate and call either negacyclic or otherwise. Some people call them different ways. So we can evaluate any lookup table that fulfills this property, because then this sign flip, it's not an issue, it's a feature. Surprisingly, this is going to be enough. So as an example, if you want to evaluate the lookup table for sign evaluation, it looks like this. You're just going to decree that if the value is below n, it's positive, otherwise negative. And exercise for you at home, this is negacyclic. I mean, just fill it in and see what happens. Now, what have we just seen? We have a blind rotation procedure that allows us to compute this. Now we've seen multiplying by monomials allows us to evaluate lookup tables. Next, as you can guess, we're going to combine the two. So I'm going to focus on the AND and NAND gate evaluation, but you can do much more with this procedure. So again, we fix some parameters. This is specific for the NAND gate setting, but you can even play with this in practice. And you encode a message as this. So again, Q over T. Except you're actually going to do Q over T times 2. You still kind of need to set T equals to 8, not 4, mostly for exposition. So a first thing we can note, we have this other lookup table now, which works as this. And the kind of important part is actually how it behaves in these cases. So if the 2 bits are equal to 1, you get a positive value, otherwise a negative 1. Like, this is very specific, but like in a moment I'll show why these values. The point here is that for the AND gate and also NAND gate, it's important that we have one distinct value for the case where the two are equal. Because if you know in AND gate, 1 and 1 equals 1, everything else is 0. Okay? Now this is what I just showed you, but this time we look at a sum of 2 messages. And now after we evaluate this lookup table, we're going to add another scalar. The whole idea is then to note the result of this, if the 2 bits are equal and equal to 1, we get something non-zero and always 0. And to fill it in even more, this is just the encoding of the product of these 2 bits. In other words, it's an encoding of the AND. This is repeated here. Another point, and this is also something you can show, L is also a negacyclic lookup table. And so we are almost done, actually. So we have these ingredients, and now we can put actually most of it together. So in gray, you'll always have what the decrypted value corresponds to, so it's a bit easier to follow along. So as an input to this AND gate evaluation, I'm going to take your 2 ciphertexts and I'm just going to add them. Then you set up the lookup table. You can think about why it looks like this, but it's not really important. And once you evaluate the blind rotation procedure on this accumulator, it's going to look like this. Now, here it's Q over 4, because it's equal to 2n over 8. Then, at the very beginning, if you remember, I said you can extract LWE samples from any coefficient of ring LWE samples. And this is exactly what we do here. And so if you decrypt now this weird ciphertext, it will look like this. And we said this is an encoding of the AND. And if you want to do NAND gate computation, i.e. unlimited computation, you kind of just flip this. Big question is, now, this is not going to be necessarily surprising, but this is a bootstrapping procedure that will output something with lower noise. The other question is, are we done? Because now we have a way to evaluate a NAND gate, and we get lower noise. Well, almost, but there's still some points to make. First, the format in which the input ciphertext were, they had modulus small q, dimension small n, and the small key. But this AND ciphertext we just computed, it's on a big modulus, big dimension, and bigger key. So ultimately the question is, can we just go back to small q small n? The answer to that is yes. First thing we need is actually yet another special key. It's called a key switching key. And this is a matrix of LWE samples encrypting a secret. I'm going to hurry up a bit. The key signing procedure looks like this. Again, this is not necessarily complex math, it's just a lot to read. So what happens is, again, we do this gadget product like with ring LWEs. The whole thing then slips inside. The sum here also slips inside. So again, what he did is evaluate the decryption circuit homomorphically for LWE samples. And so we're just going to also neglect this error term. It's just going to go into the LWE notation. Then, OK, so now we change the dimension and the key. The last thing is we need to now switch to modulus. So what we start with is like an LWE sample of like this big Q over T times M. So to go to small q, it's going to be embarrassingly simple. We just multiply by big Q, multiply by small q, divide by big Q, and round the whole thing. And this gives us simply something under mod q. You can show that this works under some assumptions. Though one thing to point out, this is like a specific example again. Quickly going to go through. Previously, when you did the decryption under the big modulus, you get this first value, which you kind of expect. And so notice the relationship is in theory just dividing by 2. Now, suddenly, now we try to decrypt, and the scaled value, well, the message should be the same, but here's no error initially. But if you actually check the right-hand side, suddenly there will be 1. And this is an error induced by the module switching in general. And from a theory point of view, this error is modeled like a Irwin-Hall distribution. In practice, it's just assumed to be Gaussian. This is the gist. This is actually a security issue that we're going to see that later. And next, this is the overall procedure. Like, we won't go through this again. But ultimately, what you have is that the noise of the output is independent of the input noise. Even better, if you choose your parameters correctly, it's going to be smaller. And this is some shameless self-promotion. You can omit the requirement that the lookup table is negacyclic with a few tricks. But like, just heads up, the whole thing still only works if the input noise is small enough. So if the ciphertext you plug into the bootstrapping have noise that's already too big, it's too late to bootstrap, barring exceptions. OK, I was well ahead of time. Are there any questions with regards to these types of scheme? There was a lot of detail. The next part has less. Any questions, comments? Yes?
At some point you mentioned that there's there's a debate or some distinction whether the circuit itself is fixed ahead of time or not.
Yeah.
Isn't this all the same case in the end if you just treat the circuit itself as input?
Yeah, but like the question is, do you want to treat a circuit as input? Because, for example, if like this, let's say, IP, intellectual property case, where I outsource some medical data analysis, I don't think the company is going to want to tell me the circuit. And so in these cases, you need like a parameterization that will allow you to evaluate anything. Whereas the case where the circuit is known is actually quite nice, because then you can do more optimizations. For example, then this will also depend on the scheme. You can then configure the parameters in a way that you never need to bootstrap, because the bootstrapping part is going to be the performance bottleneck. Yeah? Great. Now the SIMD schemes. What you've seen, we encrypt small values. Now this we didn't really discuss, but this T, so the message space we've seen, in example, it was 8 to encrypt bits. For reasonable performance, you can go up to like, say, message space, like an actual message space of 5 bits. So not super exciting. Nice thing is you can actually generalize it in a way that you can evaluate arbitrary lookup functions, lookup tables on the encrypted data. So no need to restrict to polynomials. You can really evaluate anything. But lastly are like single instruction, multiple data type schemes. We encrypt vectors of larger values. And we're going to perform coefficient-wise addition or multiplication. So like a very incomplete list of schemes. There's BGV and BFV. There you encode values from a finite field and work with those. CKKS, people will write that like they act like floating point numbers and encode real numbers. In practice, it's more like fixed point numbers, and the whole thing is going to be slightly approximate. Why? Will be shown later. But a nice thing about this relaxation to approximate arithmetic, you can encode vectors that are huge, like easily vectors of size 2 to the 16, whereas this is quite difficult with BGV or BFV. This is incomplete. For example, a very new development is called generalized BGV by someone from our lab. And then also hybrid CKS and BFV, etc. We don't really care. So in this case, since we need to encrypt vectors, ciphertexts are going to be ring LOE samples of some M prime, not necessarily of the message vector. So like what M prime is will depend on your setting. So for BFV or BGV, you're going to apply the Chinese remainder theorem, but like for finite fields. So you're going to pack a bunch of values from a finite field into one polynomial in a way that it acts in a SIMD way. And the whole point of this CRT stuff is, well, suppose we have some multiplication procedure that takes as an input and would output this. But this is just polynomial multiplication. And in general, this is not going to be really what we want. What we want to do is coefficient-wise multiplication. So we need some kind of encoding that will allow you to do that. And so yeah, applying a CRT allows you to do this. Now the special case here is CKKS, where they're actually going to interpret the input vector as something over the complex numbers and apply the inverse DFT, and then scale it, round, and plug that into a ring LOE sample. Now, intuitively, anyone has an idea why the inverse DFT, not the DFT? This is small signal processing, so. There's a difference in terms of like preservation of norms if you use the inverse first and the DFT later during the encryption. Okay, so just going to dump more equations on you. The observation is the most interesting line is actually the first one, because this is the decryption or decoding of a ring LOE sample, and we're going to multiply it because this would if you actually filled in a message here, correspond to almost the product of the vectors. Now we can expand the whole thing, etc. And then the final line, we end up with something starting with delta square. Like I really need to write it this way. I know it's not very interesting. But then you can take this expression and interpret the input basically as something called an extended ciphertext. This thing now has 3 components instead of our ring LRB with 2 components. But if you then actually compute the inner product of these terms here in this extended key, you'll actually get delta squared times the product of a message back. The problem here kind of is that we actually want delta, not delta square. So what we do, take this extended ciphertext, interpret it as like the usual numbers, not over some polynomial ring, and we just divide by delta and round. It's quite brutal. And so actually this division is not just to get rid of this squared term, but it also helps kind of decrease the noise, because we're going to divide by delta. It's going to squash the magnitude of these terms. Yeah, crucial for noise management. And to go back from this 3-term ciphertext to a 2-term ciphertext, there's a special procedure called relinearization, which also needs special keys. Right? Now, this is more intuitive and really thorough. So for one multiplication, we need to divide by delta to get rid of the noise. And in theory, you can keep on doing this, but if you keep on multiplying, the noise is still going to increase every step. So you can kind of circumvent this by setting your initial huge modulus to the product of a bunch of primes, not necessarily small. So after every multiplication, instead of really dividing by delta, you'll divide by the, well, next modulus. And this is going to squash the error for every multiplication in a way that is better than just dividing by delta. There's some analysis that I omitted. So the intuition kind of is the number of primes in the big modulus is going to represent your maximum multiplicative depth. But eventually, you're going to evaluate a bunch of multiplications, and at some point, we're going to run out of primes to divide by. So the answer is now we need to bootstrap. But we'll see that in a minute. Now, this is the most technical slide of the talk, but I just included for completeness, because addition for ring LRB samples we've seen at the very beginning. We've also seen multiplication now, but there's a third operation we care about in these SIMD schemes, namely vector rotation. So what I mean by vector rotation is you have some vector, but they have an ordering of coefficients. But now say you want to compute the sum of this vector. Somehow you need to be able to like combine the elements of different indices. And if you don't have a way to kind of rotate the coefficient of the vector, this is going to be impossible. This is what this rotation does. Okay, and now scary math. Now if you're in this ring, and you have some index t in this group, so you have usual structure, in the following map, so you evaluate this polynomial at the power of this monomial. This is going to induce an automorphism. And in fact, since it's an automorphism, if you apply it to a ciphertext, so component-wise, this is eventually going to be actually a ring LRB sample of just the message evaluated at x to the t. But careful, it's also going to be applied to the secret. Now, we'll take care of this later. Now, this is a shift theorem for the normal DFT. This is also going to apply to NTT. But the gist is, if you have like the DFT of a vector, interpret this whole thing as a polynomial, and kind of evaluate it at some root of unity, then after you apply the inverse, this is going to be actually a rotation of the vector. In practice, you wouldn't choose your root of unity in this way. It's also going to have a slightly different meaning. And then for this last point here, so that we kind of change the key, we do the same thing as kind of before. We do key switching, though with ring LRB this time. Okay, now, CKS bootstrapping is very fun, because it's also quite weird. So recall at the beginning I said CKS is approximate. Approximate in the sense if you bootstrap a CKS ciphertext, you're only going to get something that's like close to the original message. In practice, this is going to be fine, because CKS is often used for, well, evaluating neural networks. And this error is like the error between the message and encryption is like Gaussian, and a lot of networks are quite resilient to this noise. Now, where does this error come from? First, the goals here are not necessarily to refresh the ciphertext, but more to restore this chain of moduli. So you can keep on multiplying after bootstrapping, and noise management is then still going to be performed through the division by the primes. And so I'm going to show you the high-level description. Recall the input. It's going to be like some scale message with regards to the, well, this should be the smallest modulus. This is a typo. So the message in the ring RB is the IDFT of the message vector. First, we're going to homomorphically evaluate the discrete Fourier transform. This works because that's a linear transformation. So just scalar multiplication and addition, no worries there. Then we're just going to artificially set the modulus to the bigger one again, which usually doesn't make any sense. Because in the ring LB sample, what's going to happen is suddenly we'll have this term here that's going to appear. And effectively, at this point, we wouldn't be able to decrypt because we have this effectively random term. So what we're going to do is, and this is kind of tricky, evaluate the modular reduction function homomorphically, which will get us rid of this term. But now there's two primes here, and we'll see in a minute why. And then to restore the original format, we then apply the IADFT again, and that's the general blueprint. Now, the modular reduction function is not linear. It's also not a polynomial. So what people kind of do is they're going to take this modular reduction function, approximate or interpolate it with a polynomial, and evaluate that polynomial instead. And so this is ultimately also the reason why the decryption is not going to be exactly the same as the input, because we're going to always incur an approximation error. You can configure it to be as small as you want, but it's still going to be there ultimately. And so which interpolation or approximation rule you choose is dependent on the setting. Most common one is, if you heard of it, like Chebyshev interpolation, but also sometimes Hermite interpolation. Hermite interpolation is kind of used if, with a lot of trickery, you want to use CKS in a way that's exact without the approximative term, but that's out of scope. Now, who's still with me? Raise your hand. One person, two, that's fine. Your loss. Now, more practical things. So there's no more math, just really practical considerations. We have this cute little Python program here. The general question is, we want to implement some algorithm with FHE, solving some problem. What can go wrong? Now you have this nice loop here, computes the sum of the first few integers up to x. Let's just assume x is encrypted. Why doesn't this work? Don't overthink it. Come on. When is this loop going to terminate? I'm going to keep on using you. Do you know when this loop is going to terminate?
After x iterations, which is the secret method. The timing is basically.
No, that's not the issue. Again, look at this. X is encrypted. How do you determine when you terminate?
I mean, it's not a circuit independent of x, right?
That's kind of the issue, because your loop termination depends on the encrypted value. But yeah, it's encrypted, so you, as someone who executes this circuit, how would I know? So one way to fix it would, well, that's the issue. Loop termination requires knowledge of x. This is a slightly better idea. You can say, OK, I know bound on the value. So in every iteration where x is encrypted, I compute some flag, where I check this should be x max. Oh no, I lost an x. And then either the flag is 1 or it's 0, and then depending on this flag, I either add or I don't. This works. This is at least correct. It's still kind of suboptimal if x max is large, because then you might do a lot of useless iterations. And in general, even computing this flag can be expensive computation-wise. Now, then the nicest way to kind of do this, ignore the red part for now, is just to write out the explicit formula for this sum. So x times x plus 1 divided by 2. There's no loop. And this is work. This is just going to take a multiplication, so it's quite efficient. Well, there's another issue here, though. You need to divide by 2. If you're in a space where this exists, sure. But often when we say we implement some neural network where we divide by 2, this is not going to be the same as if we divide by 2 in ZQ where Q is prime. Because on one hand, you have reals, here you have integers mod Q. And if Q is the power of 2, this is not even going to be invertible. So depending on your setting, what you can do is you can interpolate this function as a polynomial. Just plug in 2 and then multiply them. One way to do it, or if you have like one of these, again, accumulator-based schemes, you can just do it via lookup table evaluation. But these are kind of things to consider. Now, general, this is kind of, if you have an interesting algorithm, it's going to have some kind of data dependency. Ideally, none in the computation sense, but in branching is a thing. So often we'll need to do it. So just some examples. If you try to implement, for example, like a Krylov solver, eventually to detect conversions, you need to bound the norm of the residual, data dependency. If you do string matching homomorphically, you need at least to know maximum string size, but this ties into what I said earlier. This is not great for performance. In general, whenever you branch on encrypted data, you might have a bad time. So there's like solutions to these, like for example, for the numerical solver, there's special solvers that have no data dependencies for conversions. They more depend on the shape of your domain. And if you branch, if you really need to branch, this is the general blueprint. You compute the flag, and then you select between the two. And ideally, you will really need to think about your problem, make some more or less reasonable assumptions, and maybe try to get rid of the branches. And if all else fails, try to turn it interactive. Sense like you can send an intermediate result back to whoever owns the secret key, and then they do the branching for you. But you have to be like, kind of reasonable with that, because the whole idea of FHE is you completely outsource something. This is sometimes interesting, but ideally you want to avoid it. Now about security, like just some few words. Okay, so for LWE, we have narrow distribution. What can go wrong? Well, obviously, if the probability that there is 0 is almost 1, if you have enough samples, you can probably just run Gaussian elimination again, be done with it. If the error is too small, like say always be below 1 or 2, you can use Grosvenor bases to attack the whole thing in an actually very efficient way. In general, even if parameters don't seem broken, they might be. I'll see how you can make sure that they're not in a minute. And there's also some less intuitive stuff. So you have the general example here. So you outsource some computation using CKKS, and you share your results with your friend. Right after the decryption, you don't really decode it. If you do it too often, friend can recover the secret key. Now, the reasons are a bit complex, but the gist is when we modulus switch in CKKS, the error that's induced depends on your secret key. Now, if you have enough exact or well undecoded decryptions, so it means you have enough of this modulus switching noise, you can derive enough information about the secret key to completely reconstruct it. And this is a practical attack. This is not just a theoretical attack. And so similar things exist for these exact schemes, like the accumulator-based scheme, TFG, FFGW, BJEV. But they're more complicated, and I think the setup is somewhat unrealistic. There's that. Some privacy aspects now. So in general, we want to keep things private. So indeed, ciphertext will not yield anything about the input data. Great. The issue is it can leak information about the actual calculation. So just as kind of a stupid example, if my modulus is a power of 2, have the ciphertext and I multiply it by 2, the least significant bit of the ciphertext is going to be 0. So this will already tell me, oh, at some point we multiply by 2. Depending on the setting, that's an issue or it's not. If you care about the intellectual property preservation, etc., this might be an issue. And so there's special techniques to fix this and ensure secret privacy, usually called like FHE standardization. They are not cheap. They're quite computationally expensive. Another issue by itself, if you don't use, like, for example, zero knowledge proofs, you have no guarantee that whoever's evaluating something actually evaluates the thing you want it to. So that's also a consideration you need to keep in mind. In general, you can't do anything against users fucking up. Sorry. So, like, I mean, in this example, someone would just keep on sharing the decryptions. You can't really protect from that unless really tell them they shouldn't. Right? Now, some FHE libraries. Now, since I like XKCD, there's obviously a fitting comic, because there's not just one FHE library. This is a non-exhaustive list. It's TFHRS, formerly Concrete. A startup in Belgium, like not just Belgium, called Zama. There's OpenFHE, primarily by Duality Tech, a startup in the US. Seal is from Microsoft. Heon used to be an FHE library. I checked last week, I can't find their GitHub anymore. So I'm not sure what happened. And then there's like really a bunch of other libraries. There's Latigo, written Go, okay. And it's really, there's a ton of them, and you will kind of need, if you implement these things or you want to use it, you really need to think about what you need. So for example, TFHRS is going to be a very efficient implementation of TFHE and FHEW. But quite often, for example, if you need to combine schemes, which just can happen, maybe OpenFHE or Seal or whatever might be better. I work the most with OpenFHE, so it's the one I prefer. That doesn't mean it's the best. Hello. Okay, now, there's a bunch of parameters. And I said we somehow need to make sure that the parameters don't break your security. So the major tool to do that, and I think it's the most common tool to do this, it's just called a lattice estimator. It's written in Sage. So kind of a Python superset. You, like no one's talked about it, seem to disagree.
Not technically a strict superset, but it doesn't really matter.
Yeah, like this is a more intuitive explanation. And it's very easy to use, actually. So this is just an example. So you just define your LW parameters. So the dimension, modulus, standard deviation of your distribution. You construct a distribution, construct a distribution of a secret key. In this case, a binary key, like we saw earlier. Set up a parameter set and run the estimator. Like, not complicated to use, and an installation of the estimator is also quite easy. It's going to output you a table like this, which a bunch of other columns I cut off. And this value here is kind of going to give you the security parameter. And also specific to an attack method, or like lattice reduction method. So ideally, when you use this, you want your security level to be like 2 to the 128 or beyond. What happens if you plug in a bad parameter set? Like here, this is kind of artificial. We have an LW, like the secret has a Hamming weight of 8. So effectively, most coefficients are useless. And then table will look something like this. Obviously, some attacks will not really apply because they're not suited for the setting. But then, for example, all other values, they're tiny. And this parameter set stems from some paper. And if you actually run the attack, it takes 2 minutes on my laptop. So even though this might still seem big, it's very easy. Other useful tools, so you have Intel Haxel. They implement fast polynomial multiplication, or rather fast number theoretic transforms using AVX 512, like specifically IFMA. It's quite easy to use, though it's written in C++, depending on whether that's your preference or not. Could be an issue. There's also Rust bindings that work sometimes. In general, for FHE, what's quite useful is Sage, because it's very easy to sketch things without needing to set up your whole math backend for FHE. And so this is kind of the end, just some interesting research directions. Well, I find them interesting. In our opinion, blind rotation seems very complicated for ultimately what it does. It boils down to computing in a product in the exponent. Feels very complicated. Another thing to point out is we use ring GSWs. If you remember from the previous talks, there's also like a thing called ntrue you can use to encrypt. And you can also use that to do the blind rotation. And this roughly gives you a performance improvement of factor 2, because you only ever work with one polynomial. That's one way to do it. Question is, what else could we use to make it more efficient? Another avenue, performance gains is hardware acceleration. There's some companies and startups already working on this. In general, my issue, and so what could be interesting is kind of do a meta-analysis, because a lot of people don't actually publish their parameters. So it's kind of difficult to tell whether some method is going to be better than another. Also, if people don't publish their parameters, it's difficult to establish whether the parameters they use are actually secure. And then some final disclaimer. There's a big symbiosis between FHE and machine learning. So a lot of press releases or papers may overhype their results. This is annoying. It's fine if you keep it in mind. All right, this is it. Now, I included every reference at the end, but if you have any questions, please let me know.